and Robert Ember, how NASA is involved in these activities and some of the work we're planning as part of this excellent initiative. So first, we wanted to start at the big picture. Our group at NASA Goddard Space Flight Center is primarily focused on how we can leverage satellite information as well as other available data to better understand landslide hazard at a multi-scale approach and moving into the arena of exposure as well. And so we've been able to do this looking at very local scale studies, mapping landslides, as well as susceptibility modeling. We've done this at a regional scale with looking more broadly. And then we have a global effort, a global landslide hazard assessment for situational awareness model, or which we call LASA. And that has helped us to increase our awareness of areas which might be at higher hazard. And we can do this dynamically every 30 minutes around the world. So starting at that big picture first, I wanted to just introduce some of the global models that we've been using and the relevance they have for local scale analyses as well. So the model that we have employed, LASA, leverages satellite precipitation information. This is right now from the Global Precipitation Measurement Mission, or GPM, which is led by NASA and the Japanese. And then we integrate that with a susceptibility map, which we've developed at a global scale at 1 kilometer resolution. And so what that allows us to do is combine this information through a decision tree, which you see on the right, to allow us to indicate areas at a 1 kilometer resolution that may have moderate or high, what we call a nowcast, or near real-time assessment of landslide hazard. And the latency of this information is based on the availability of the satellite data, which is about 4 hours after satellite acquisition. And so I'm just showing here an example of this LASA output. This is a storm passing over, a hurricane passing over Mexico, Hurricane Willa. And so you can see the kind of dynamic characterization of hazard as this storm, which you see is the GPM precipitation information makes landfall. And so we've recently published, just last month, a new version of this model that leverages machine learning approaches to get a more probabilistic assessment of landslide hazard. But this gives you a sense of how we can use satellite precipitation, soil moisture, snow information, and other products to get a better handle on the landslide hazard regionally, and of course using static variables such as lithology and then slope as well. Now, focusing more on the high mountain Asia region, we've had several studies in this region already, mostly span kind of what we call the high mountain Asia region. And so we've been doing landslide mapping or inventory analysis based on media reports, and these are the dots you see here, as well as other mapping activities to identify the hotspots within this region at a bigger picture scale. And so one of the recent studies that came out recently from our team is how we can take LASA, the global landslide modeling system, integrate that with actually future precipitation projections provided by the National Oceanic and Atmospheric Administration, or NOAA, in the US. And so we combine this information first to look backwards and compare where we expect landslide hazard at a decadal scale, and then forecast that into the future, looking at 2060 to 2100, to see where we may have changes in landslide hazard, elevated changes, which is what you see in the dark colors on the top, and in terms of changes in precipitation extremes. And so the map that you see here highlights also the current location of glacial lakes. And so this fairly preliminary study highlights the potential for better understanding future anticipated hazard at a regional scale. We're not looking locally at this point, but we understand that there could be accelerated increase in hazard due to changes in extreme precipitation, specifically rainfall, in the monsoon season. And so these model outputs are available. And so the goal with some of our other work that's related to this, that will be funded, that is funded through NASA, is to look at this climate scale impact of landslide hazard. And so we're hoping to advance this and work closely with you as this complementary research is undertaken. But more specifically for this work, I wanted to highlight some of the algorithms that we've developed, specifically my colleague Pukar Amatya, to improve our understanding of how to map locally using high resolution information from commercial data, including the planet data set. And so the semi-automatic landslide detection system, or we call it SALAD, is an open source system that is currently going through the code release process at NASA, led by Pukar. And it's configured to run so that we use machine learning approaches, specifically random forest machine learning, as well as some training data set, but mostly semi-automatically implementing machine learning methods to map landslides. And so one example of this is a time series that Pukar put together for the Arnaco and Pasalamu highways from 2009 to 2018. The black indicates the locations of the landslides that were mapped. And on the right, you see the Jur landslide and the evolution of that landslide as seen by planet data over time. And on the top, you see an image from Landsat from that event. And so you can see the impact of the earthquake, as well as some of the recovery information afterwards, but the increased presence of landslides following the major earthquake. Now we're taking that mapping information, which we will be doing for a multi-temporal view for the study area that we're talking about here. And we're going to be using some additional machine learning methods based on map landslides to develop new susceptibility analyses. So this is work that we just completed for the World Bank focusing in northern Morocco. So there was a landslide inventory developed and then a landslide susceptibility map developed by Robert Emberson of this team. And so we have new approaches to leverage the satellite observations as well as local data sets to better ascertain the potential susceptibility of landslide locations and initiation points within these areas. And this is all done through satellite mapping. Another example that Robert has recently published is a study done for a local area within Bangladesh in the refugee camps. And so this shows not only the landslide hazard level, and so he did a modified local version of LASA, based on local inputs, a 10-meter digital elevation model for the southern camp. But in addition, we looked at exposed assets. And so this map on the right shows you exposure to roads, so where higher or moderate hazard intersected roads. We're also able to do this for infrastructure as well as population to assess the exposure as well as the risk for these local analyses. So just to conclude, in terms of the involvement of NASA and Pukar and Robert's contract, the USRA, within the Upper Arun Hydropower project, it's threefold. The first is to do extensive landslide mapping with the goal of creating multi-temporal landslide inventory maps using the algorithm we developed, as well as high-resolution optical imagery, primarily from the Planet archive. We will be conducting landslide modeling in twofold. First, looking at susceptibility mapping, likely using random forest mapping machine learning techniques, as well as doing some runout modeling using an empirical scheme called FLOW-R, or a modified version of that, to start to look at not only where these landslides may have initiated or where they may be initiated, but ultimately where they may go. And then lastly, an important tenet of this project is capacity building. And so all of the code that we're developing is open source, or will be, and that will be transferred to relevant stakeholders with trainings to improve uptake and use of these models, not just the products that come out of it, but the models that we are able to run in different regions as well. And so really training at the university level as well as with this community, how these could be used in the future. So with that, I'd like to thank you. We have several new publications on this work. If you're interested, we'd be happy to make that information available to you. And we're extremely excited as a team to work on this project. I unfortunately may not be able to stay the whole time, but my colleagues, Robert Emberson and Pukar Amatya, will be on to address any questions later in this discussion. Thank you so much.
Thank you, Dr. Dahlia, for nicely outlining the overall work and how this technology can be used for mapping landslide susceptibility with examples from different regions. It's really appreciable and we highly appreciate it. To continue with the understanding the technology for addressing the disaster risk, we have another presentation from Dr. Christine Cook from Potsdam Institute for Climate Impact Research in Germany. She will be talking about GLOF risk assessment. Dr. Christine?
Yeah, thank you. Thanks for inviting us to give a presentation and for the introduction. I will clarify we're actually from the German Research Center for Geosciences, which shares a campus with the Potsdam Institute for Climate Research. That is a different institution. Okay, so I will share my screen. And then, okay, so I hope that everyone can see the slide here.
Yes.
Yeah, so what I want to present is a different type of technology or technological advance that we are working on that also aims to provide some warning for events, but in a different way than what Dahlia was talking about. So rather than go in kind of the forecasting or predictive way, what we're aiming to do is actually rapid detection. And from rapid detection, issuing early warnings for events like glacial lake outburst floods, landslide lake outburst floods, and other catastrophic flow events. Because these events are traveling downstream through a catchment, and they're moving pretty fast, but not that fast, if we can detect them very quickly after they initiate, we can actually provide from, depending on where vulnerable places in the catchment are, we can provide from tens of minutes to even hours of warning. And so we aim to do this using seismic methods. And so in our group at the German Research Center for Geosciences, or GFZ, we have been working for a number of years on trying to advance the use of environmental seismology. And so environmental seismology refers to using seismic data to observe and monitor processes that affect the Earth's surface. So typically seismometers are installed to look at earthquakes, to monitor earthquake activity, but actually all sorts of processes produce seismic energy. And basically anything that transmits energy to the Earth's surface will create seismic waves, and these can be measured and interpreted. And so here in this slide, we just see on the right some examples of seismic data from different types of events. So at the top, here's a rockfall. In the middle, a regional earthquake, and then a debris flow. And kind of what we're interested in here in the bottom, this is fluvial sediment transport. And so each of these types of events produce distinct signals, and signals that can potentially be measured at a distance. And so in particular, if we look at the signals produced by rivers, which we can call fluvial seismology, we can see a lot of promise for the monitoring and detection of particularly destructive events. So one of the huge advantages that seismic methods have is that it's a remote type of method. We do not have to install an instrument in the river. We don't even have to install an instrument very near the river. And so this is a real advantage if we're trying to monitor and provide warning for destructive events. One of the problems with kind of traditional methods of doing flood early warning in high mountain areas is that the instruments get destroyed in the floods that they're trying to detect. With seismic instruments, we can actually put them in safe locations far from the river, and yeah, to help ensure the continuity of a system in case of a big event. And so here as an example, I'm showing some data from an event that happened in the Bodakoshi-Sunkoshi River in July of 2016. So this was a kind of medium-sized outburst flood that came down this river. We can see a before and after photograph appear. This event destroyed all of the gauges in the river. So here's an example of a pressure gauge that we had installed that was nowhere to be found after the event. And then in this very colorful figure down here, this is the seismic record of this event as it passed by a station that we'd installed in this catchment, actually to look at aftermath of the Gorka earthquake. And so with this data, we can gain a lot of information about this event. We actually had a whole array of stations in this catchment. And with near river stations, we can actually track this flood as it moved downstream. So here's the seismic signal of this event. And here we can see its arrival moving downstream as it's passing station after station after station. And so this is nice. This shows us that certainly if we install seismic stations near a river, they can kind of act similar to a gauge, a water level gauge, but can be put in a safe location. But what was more interesting to us is that we could actually see the seismic signal of this flood at stations much farther away. And so here I'm showing two examples of this. So in the top, here is a station that was 25 kilometers from the source of the event. In the bottom, this is the station that's 60 kilometers from the source of the event. And we can see this kind of blob of warm colors in both of these records. And this is basically the full event. So with these far field stations, we can actually capture the initiation of this outburst flood, and we can track it through its dissipation into background discharges. And so this was really exciting because if we can detect an event like this at a station 60 kilometers away, this means that with relatively few seismic stations throughout a region, we can potentially detect very quickly events of this type. And this raises the potential to use this for early warning. So here's just another example. This is a quite old cloth from 1994 in Bhutan. And here we're just seeing the seismic record of this event from a station that was 93 kilometers away from the Gloff source. And again, it produces this blob of warm colors here. It's a very distinct signal that can be detected over quite long distances. And so we've made a bit more progress on this over the past few months, following this February 7th, 2021 landslide debris flow hazard cascade in Uttarakhand. And so many of you have probably heard about this event, but just to sum it up, basically there was a large rockfall here that fell into the valley floor and triggered a mass flow that traveled down the channel and eventually evolved into a debris flow and then a flood as it transited down channel. And so here's just a video of what this looked like around here. And so this was quite a destructive event and quite a large one. And for our purposes, this helps us to make progress on the potential for seismic early warning of these events because it occurred within a pretty dense seismic network operated by the National Geophysical Research Institute of India, who've been working with us on this. And so what we've been able to do is actually look at the seismic records across this entire network of this event and evaluate what are the detection limits, what can we do with this event, and what is the potential for early warning. And so here I'm just showing 4 examples of the seismic data from stations at different distances across the network. This event was a bit complicated because it did have this initial rock slide and then more concentrated mass flow before transitioning into a more flood-like phase. And so we can look at the detection limits for these different types of events or these different phases of this one event. And when we do that, what we can see is that first the rock slide was extremely energetic. It's easily detectable across the entire network and actually in far field stations 1,000 kilometers and further away. So events like these, large landslides, large rock slides, can be fairly easily automatically detected and located using regional seismic networks. Now the mass flow phase of the event, so this is this more concentrated phase. This can be also detected pretty well across the network. As we get into stations to about 200 kilometers away, the energy of the event starts to approach the background noise level at some of the stations. And now it's really the third phase of the event that's most interesting for us, as this would be the most similar to what we would expect from, for example, a GLOF or a landslide lake outburst flood. And here we can see that this phase is detectable over some distance, but not over the entire network. And so we can see up to about 100 kilometers. There are some stations that can clearly register it, but at other stations, it starts to fade into the background noise. And so this is just a function of where the stations are installed, how close they are to, this tells us first what channel it's in.